Good morning, Year 12. So I hope you've had a good weekend. So before we start this video, I just want to check that we're up to date with everything. So we're on chapter 18, Trigonometry 2. So you should have done exercise 1.1, which is changing radians to degrees and degrees to radians. And you should have done exercise 1.2, which is finding the lengths of arcs and the areas of sectors using the radians formulae. Okay, so that was last week's, the week before's lesson actually. And then last week we looked at inverse trig functions, and I asked you to have a go at exercise 3.1 on page 264. So any issues with any of those, please email me and I will do my best to help you. Okay, so what we're going to look at to start with, we've got this starter here, which is just sort of going over some of what we've done already. So what I'd like you to do is copy that table out, fill in, first of all, fill in the radians, equivalents to these degrees, and then fill in the sine, the cosine and the tan. So this 45 you should know, but 120, 135, 270, 360, you're going to have to work out using your knowledge of 30, 45, 60, 0 and 90. Okay, so please try not to use a calculator for this. Try and see if you can work it out. It's really important that you can work out these ones from your graph. Okay, so I've drawn here, sketched here for you the sine, the cosine and the tangent graph to help you. You might want to just sketch those in your book as well. So press pause, have a go, see if you can fill in that table, and we'll go through it again in a minute. Okay, so let's start with just filling in the radians. So remember, pi radians is the same as 180 degrees. So that's always our starting point. Okay. So 45 is going to be a quarter of 180, so we'll call that pi by 4. 120 is 2/3 pi. Okay, so if we divide pi or 180 into 3, you get 60, so times it by 2, you get 120. Now 135 is actually 3 lots of 45, so that's going to be 3/4 pi or 3 pi by 4. Okay, 270, well that's bigger than 180, it's 90 bigger. Okay, 90 is pi by 2, so this is 3 pi by 2 or 3/2 pi. Okay, and 360 is 2 lots of 180, so that's 2 pi. Okay, so hopefully you've got those ones done. So we can fill in 45, hopefully fairly straightforward. Sine of 45 or pi by 4. Okay, remember this is the one you can write in two different ways. It's either 1/√2 or it's √2/2. Doesn't matter which one you choose. Okay, one will be easier than another depending on which calculation you've got to do. And cos is exactly the same. Okay. Okay, so cos is also 1/√2 or √2/2. And then tan is just 1. Okay, so 120, like we said, isn't one we know necessarily. But so what we've got to do on our graphs is we've got to work out where 120 is. So it's around 90s here. Okay, so 120 is here. So I need to work out the difference between 180 and 120, and that difference there is 60. Okay, and because of the symmetry of the graph, that will be the same as the distance from 0. So 120 on the sine graph is equivalent to, or sine 120, sorry, is equivalent to sine 60. So if you remember, sine 60 is √3/2, so sine 120 will be √3/2. Okay. And remember, the rule with the sine is you do 180, take away that the value that you're looking for. Okay, so let's do the sine again. So 135, well 90 is here, 135 is a little bit further on. Okay, so if I do 180 take away 135, I get 45. Okay, so again, that difference there is going to be 45. So doing sine 45, which we've said already, is 1 over root 2. Now, 270, okay, is this point here. So there's nothing else like it. It is just minus 1. And 360, or 2 pi, is at the end, so it's 0. Okay. So let's have a look at the cos graph now. So cos 120, well, this goes up to 90 here. Okay, and cos 120 is going to be around here. Okay, so it's going to be a negative number to start with. So let's get a negative sign in ready. Okay, what's it equal to? So it's equal to a value here. Okay, and it's going to be, the difference here is 30, so the difference here must be 30. So we're looking for 60. Okay, so again, it's going to be equivalent to cos 60, but it's going to be the negative of it. Cos 60 we know is a half. Okay, so therefore cos of 120 is going to be minus a half. Okay, so if we look for cos 135, so we've got 90 here, so 100, 10, 20, 30, 35 is going to be about here. Okay, and again, because of the rotational symmetry, there's going to be a value somewhere over here. That is going to be the positive of this value here. So again, I know this one's going to be negative, so I'm going to put the negative in first. Now the difference from 90 to here is going to be 45. So that's going to be the same as this distance here, 45. Okay, which tells me actually this value here is 45. So I should know that cos 45 is 1 over root 2, or root 2 over 2. So this is going to be the negative of that. So it's the negative of 1 over root 2, or root 2 over 2. So 270 is one of our key values. We've got 0, 90, 180, 270 is here, so that's going to be 0. And then 360 is another key value. Okay, it's where the graph cycle ends at 1. Okay. Alright, so then if we move on to the tan graph, just move that up a little bit so we can see it. Okay, again, tan 45 you should know is 1. 120, so at this point here is the asymptote at 90 degrees. So 120 is here, and again I can see it's negative, so let's get that ready. And again we have that rotational symmetry about 90. So there is going to be an equivalent value over here. Okay, that is the same, is the positive answer to this one. Okay, so this is 90, this is 120, the difference there is 30. So we've got the same difference here, 90 down 30 takes us to 60. So tan 60 is the same as the negative of tan 120, or tan 120 is the negative of tan 60, is a better way of putting it. So tan 60 is root 3, so 120 is negative root 3. Okay, 135, same idea, let's just clear that off there. So 135, again, is going to be a negative value. It's going to have an equivalent over here. Okay, that difference there is 45, which means this difference here is 45, and the value we're looking here is 45. So this is the negative of that. So we know the answer is negative. Tan 45 is 1, tan 135 is negative 1. Okay. Now, I haven't got 270 on this graph, it only goes up to 180 because of the pattern repeats. So I'm going to do 270 take off 180, which is 90. So tan 270 is the same as tan 90, and 90 is infinity. So 270 would also be infinity. 360 take off 180 is 180, and tan of 180 is 0. So tan of 360 will also be 0. So hopefully you've got a lot of those right. If you are struggling with those, then it just comes with practice. But it's a sort of thing you can make up the questions yourself using multiples of 30, 60 and 45, and also the 0 and 91 key ones. And you can always check them on your calculator. So if you didn't get many of those right, that is something you can practice on your own. So today's lesson is looking at approximations for trig graphs for small values of x. Okay, so I'm going to start by looking at the trig graphs. So let's get those up quickly. Okay, so I've got all three trig graphs there. I'm just going to get rid of two of them. So we've just got y equals sine x. That doesn't look like y equals sine x. If I just zoom out a little bit, okay, you will see we've got y equals sine x. But what we're interested in is the section for the very small values of x, so 0.1, 0.2, 0.3 radians. Okay, and often we don't necessarily always need an exact answer. We want an approximation. So if I just quickly draw in the graph y equals x, you can see for those very first few values, y equals x and y equals sine x pretty much lie on top of each other. Okay, so actually y equals x is a good approximation for sine x. So if I knew my angle was very, very small, and I just wanted to approximate sine x, I could actually say, okay, it's like the graph y equals x, so sine x can be approximated by x. So for example, if I wanted to do sine of 0.1 in radians, then I'd say sine of 0.1 will be 0.1, okay? And this is only in radians, this only works for radians. So if I wanted to do sine of 1.5, I'd say, okay, that's equivalent to about 1.5. So it's only an approximation, but and it only works for small values of x, but it is very, very useful. And if all you need is an approximation, it's a pretty good method to approximate. Okay, so that's the sine graph. So let me just get rid of that one for a minute. We're going to look at the tan graph next. Okay, so this is the tan graph here. Okay, again, only looking at small values, so 0.1, 0.2. And again, I'm going to draw in y equals x. And you'll see again, for y equals x, all right, and the tan graph, for very small values of x, they are equivalent. So again, tan 0.1, I would say, is about 0.1. Tan 0.2 is about 0.2. Okay, so the one we haven't looked at is cos x. Okay. Okay, so if we look at the y equals cos x graph, well, if I put y equals x on again, it's quite obvious that that's not a good approximation for y equals cos x. So we need to be thinking of something that looks like this shape here. Okay, so a parabola looks like this shape if it's a negative x squared, all right, but it would normally start down here. So in order for it to be crossing up 1, it needs to be 1 minus x squared. And in fact, the one that works best is 1 minus 0.5 x squared. And you can see, got a really close fit here, pretty much all the way to 0.6. Okay, so it's a really good approximation, okay, for those small values. So we've got that sine x, it can be approximated by x, and tan x can be approximated by x, and cos x is approximated by 1 minus 0.5 x squared. So let's write this up in our notes, okay? What we've got here is, first of all, it only works for small values of x. It only works when we're measuring in radians, okay? So sine x is approximately equal to x, tan x is approximately equal to x, and cos x is approximately equal to 1 minus a half x squared. So you will need to know those off by heart. They will appear as questions in their own right or part of another question. And this is new to the new A level, so it's one of those questions that's likely to come up in the next few years, so you will need to make sure you've learnt those. So let's have a look at some examples. Okay, so this one says, calculate the percentage error if 8 degrees in radians is used in approximation for sine 8 degrees. So at the moment this is in degrees. Our approximations only work if we're measuring in radians, and it does say in radians here. So the first thing we really need to do is get 8 degrees into radians. So if you remember, to get degrees into radians, we divide by 180 because that tells us the fraction, and then we multiply by pi. Okay, so I'm going to do that on a calculator. Okay, 8 divided by 180, okay, multiplied by pi, gives me 2 over 45 pi. Now I'm going to store that into memory A. Okay, so that's there. So, and I'm got to work out percentage error. So percentage error, we look at the absolute error. What is the difference between 8 degrees in radians, or 2 over 45 pi, and sine of 2 over 45 pi? What's the actual difference? Divided by the correct value of sine 2 over 45 pi, and then we multiply that by 100. Okay, so let's start with sine of 2 over 45 pi. So if I do sine, I know that answer's in memory A, so that's sine A. That's the actual value. I'm going to subtract my approximation, which is just A, because we're saying that these are A approximates sine A. And that gives me minus 4.5 to the times 10 to the minus 4, so a very, very small number. I'm going to divide that by the actual value, which is sine 2 over 45 pi, which is in A. And we get minus 3.25 times 10 to the minus 3. Now that's the absolute over correct. If I want it as a percentage, I need to multiply it by 100. And we get minus 0.325. Now it's minus because I did the smaller value take away the bigger value, and we're actually just interested in the actual error, not which one's bigger. So the percentage error, we're going to ignore the minus, is actually 0.325%. Okay. So let's have a look at another example. So this one, we've got in this triangle, theta is 1 degree. So this is degrees at the moment. And x is 2.5 kilometres. And it says, calculate the height of the triangle in metres using an approximation for tan theta. Now, if you do this without doing an approximation, you'll get no marks because it's been very clear that you must use an approximation. Okay? So, first of all, this is in degrees, we need it in radians. So let's start with that. It would be 1 over 180 times pi. Okay? And again, I might just get that straight into my calculator. So 1 divided by 180 times pi. And that's an 80th pi. So I'm going to store that, and I'll put it in B this time. Okay, so that's stored in B, an 80th pi. So that's the angle. This is 2.5 kilometres, and I want to find this one. So I need to use my trig ratio. So this is the opposite and this is the adjacent. So I know that tan theta equals the opposite over the adjacent. So in this case, y over 2.5. So to find y, I'd need to do 2.5 times tan theta. Now I'm going to use an approximation that tan theta is theta, so it's going to be 2.5 times theta equals y. Now theta, we've said in radians is 1/80th pi, so it's going to be 2.5 times 1/180 pi, and that equals y. So let's put that onto the calculator. So I already got 1/180th pi there, so I'm just going to multiply that by 2.5. Okay, and we get the answer as 1/72 pi, so let's get that as a measurement 0.043. So y equals 0.043 kilometres. Okay, so it's actually 0.436 kilometres. Okay. So that looks a really small number, but if you think that this is only 1 degree and this is 2.5 kilometres, 1 degree is going to give you a much smaller height on the triangle. Okay, so key, it has to be in radians, so if you're given an angle in degrees, convert it to radians straight away, store it on your calculator, and then remember your approximations. Tan theta is about theta, so do that substitution. Okay, and then solve your equation from there. Okay, so what you need to do now is turn to page 261 and 262 and have a go at exercise 2.1. Okay, so you might want to just copy out the example given there as well, and then have a go at exercise 2.1. Any problems, just email me and I'll try and help you best I can, either by email or with a video. Okay, have a good week. I will be setting you more work in the week.